The next module in HSC Physics is Module 6, Electromagnetism. In here, you'll be focusing on developing and evaluating questions and hypotheses with designing and conducting investigations, and obtaining data and information to solve problems about electromagnetism. In this module, we'll be taking a deep dive into the world of electromagnetism, including looking at electric fields, with this time a focus on how particles are affected by them. You're back with using electric circuits, except this time you'll be focusing on how wires move when in contact with a magnetic field. You'll merge the two ideas together in how electric fields and magnetic fields relate to one another. You'll look into how technological advances and everyday machines use the effects and laws inside this topic. And there's a lot of equations in this topic with a lot of maths to wrap your head around. The first topic is called Charged Particles, Conductors, and Electric and Magnetic Fields. This topic is about electric and magnetic fields, but these fields have similarities to gravitational fields, and so these will be used for comparison. The inquiry question for the first topic is, what happens to stationary and moving charged particles when they interact with an electric or magnetic field? In here, we will look at stationary particles and moving charged particles such as electrons or protons, and we'll see what happens to them when they interact with electric or magnetic fields. 1.1 asks students to investigate and quantitatively derive and analyze the interaction between charged particles and uniform electric fields, including electric field between parallel charged plates, E equals V over D, acceleration of charged particles by the electric field, F net equals MA, F equals QE, and work done on the charge, W equals QV, W equals QED, and K equals half into MV squared. So what are uniform electric fields? If a set of positive and negative charges were lined up in two rows facing each other, as shown in the diagram, the lines of electric field in the space between the rows would be evenly spaced. The value of the strength of the field would be constant, and this is called a uniform electric field. So let's look at the electric field strength. Two parallel charged plates connected to a potential difference produce a uniform electric field of strength. E equals V over D, where V is the potential difference or voltage in volts. D is the perpendicular distance between the two parallel plates in meters. E is the electric field strength in volts per meter or Newton per coulomb. Note that D is strictly the difference between two charged plates. It is not dependent on the position of a particle within the electric field. The direction of such an electric field always goes from the positively charged plate to the negatively charged plate. This is shown in the diagram. Now, let's attempt example 1 to find the electric field strength. What is the electric field between two plates 5 centimeters apart connected to an 100 volt DC supply? For the solution, firstly we'll write down our given data. So the voltage is 100 volts. The distance is 5 centimeters, which we'll then have to convert into 0.05 meters. So the electric field between two plates is found by using the formula E equals V over D. We'll substitute our values in, and we get 100 over 0.05. And thus, our answer is E is equal to 2000 volts per meter. Now, let's find out how a positive charge and a negative charge behaves in an electric field. A charged particle experiences a force when in an electric field. Positively charged particles are attracted to the negative plate, and negatively charged particles are attracted to the positive plate. So remember, here opposites attract, just like the magnets. The magnitude of this force acting on the charged particles is given by the equation Fe equals Qe, where Q is the charge of the particle measured in coulomb. E is the electric field strength in volts per meter or newtons per coulomb. F is the force measured in newtons. Direction of force depends on the nature of the particle's charge. The charge of the particle is either given by the question or provided in the datasheet. Now, let's look at graphing electric field strength. By Newton's second law, F equals ma, any charged particle in an electric field experiences acceleration. Hence, their change in displacement increases with time. Path of motion is curved and not linear. A is a voltage distance graph. And when you are graphing electric field strength in B, it equals the gradient of the voltage distance graph, as shown here. So, how do we calculate the work done on a charged particle in an electric field? Let's find out. When charges move in an electric field, something has to do work to get the charge to move. Since the force acting on a charged particle can be determined by its charge, C, electric field strength, E, potential difference between charged plates, V, and distance between them, D, work done can be expressed by W is equal to Fs. Substitute force with QE and displacement S with distance D between a pair of charged metal plates, and we arrive at W is equal to QED. Alternatively, D can also be expressed in terms of electric field strength and potential difference across the metal plates. D is equal to V over E. When you substitute this back into the work equation, we get W is equal to QE in the brackets V over E. By cancelling both E's, we get W is equal to QV, where Q is the charge of the particle in coulomb, V is the potential difference in volts, and W is the work done in joules. Work done to move a charged particle against the electric field is shown in this diagram. As you can see here, moving a positive charge from the bottom of the negative plate to the positive top plate requires work and raises the voltage. Work done by electric field can be analysed by a change in kinetic energy of the charged particle. W equals delta K, which equals half into M into brackets V minus U whole thing squared, where M is the mass of the charged particle in kilograms. U and V are initial and final velocities of the charged particle respectively in meters per second, and K is the kinetic energy in joules. So, let's tackle the next question. Given that an electron is accelerated from one plate to another, the voltage drop between the plates is 100 volts. Find A. How much energy does the electron gain as it moves from the negative plate to the positive plate? B. How fast will the electron be travelling when it hits the positive plate if it left the negative plate with zero velocity? Let's start by writing down the given data of the question. So we'll know that V is equal to 100 volts. And from our data sheet, we'll know that the electron mass is 9.1 times 10 to the power of negative 31 kilograms. And the charge of the electron is equal to 1.6 times 10 to the power of negative 19 coulomb. So for A, to find the electron energy gain, we can use the formula W is equal to VQ. Since we know the voltage and charge, by substituting the values in, we'll get to W is equal to 100 into 1.6 times 10 to the power of negative 19. Therefore, the work done is equal to 1.6 times 10 to the power of negative 17 joules. For B, the energy gained as kinetic energy is EK is equal to half into mv squared. Rearrange the equation in terms of V, and we'll get V is equal to the square root of 2 times EK over m. By substituting the values in, we'll get to V is equal to the square root of 2 into 1.6 times 10 to the power of negative 17 over 9.1 times 10 to the power of negative 31. Therefore, V is equal to 5.9 times 10 to the power of 6 meters per second.